Yeah, okay, good. Um, well, I guess I can get started a little bit early. So again, it's very nice to be here. And yes, this works great. I want to talk about some work that I was doing with my graduate student, one of my current graduate students right now, Abe Shrestha, who's listed down here at the bottom. For a very long time, it's been work in progress, and we finally managed to get it out, and I'll show you why. It took so long as we go forward. But you can read a lot about what I'm about to tell you today in this archive preprint, which came out it's a little bit earlier this month, end of last month. This picture here that is on front of my slide, this is a contour integral that will play an important role later on in the talk. It's part of a rather technical argument. So I want to start with some kind of generalities, try and show you my motivation for why I'm working on these things. It's a little bit distinct, I think, from the central thrust of this conference, but I'll try to tie it into ADS-CFT as much as I can. The punchline of the talk is sitting right here in the title. It's the idea that these conformal surface defects, and I'll explain what I mean by those, in four dimensions, in four-dimensional Maxwell theory are trivial. All right then, so let's get started. So the cartoon version of my talk is the following question. I have some photons, which I've drawn as a 5-year-old might as the sun, and I have some electrons on a wire that are moving around, and I want to introduce some kind of coupling between the charged electrons and the photons in the bulk. So the electrons have to go up and down the wire, and they interact with the photons, which are free to travel in 4D. And so I just note before going forward that the surface in the title of my talk, that's a 1 plus 1 dimension. So it has one spatial extent, one time extent, just like this wire has one spatial extent, one time extent. So it's really the same system as in the title. And I want to ask, if I couple a photon to charged matter on a wire, can the system flow to a non-trivial conformal fixed point, in the language of Wilson and other people, under the renormalization group? And the answer I want to give is a simple no. Okay, there are lots of assumptions buried in that statement, and there's a lot of detail in the argument. I guess there are some comments going up on the 1 hour for the presentation questions. Right. Yeah, and if you have questions, please put them in the chat, and I'll try and pay attention to what's going on and answer them as they come up. I welcome interruptions. Okay, so some assumptions about what I'm saying and some background material. So a photon, right? A photon in 4 dimensions, it's got a lot of symmetry, as you probably know. It has Poincare symmetry, but it also has special conformal transformations, and it has dilatations, and altogether, the photon in 4 dimensions is well known to have this conformal symmetry, SO4, 2. Now, if I put a wire in this system, I clearly am breaking some translational symmetries, and so this symmetry group has to break a little bit. But I want to break it as little as possible, and so what I want to preserve is I want to preserve an SO2, 2 cross SO2. So I want to preserve a residual conformal symmetry group for the degrees of freedom on the wire, and I also want to preserve rotations around the wire, an SO2 or U1 rotation around the wire. And when I say I'm looking for fixed points under a normalization group, I'm looking for fixed points with that symmetry. So I have nothing to say about theories which break more than that symmetry, which are non-relativistic and so forth. They may be very interesting, but the techniques I'm going to use I can't make any clean statement about those. It's a statement about fixed points under the normalization group with that symmetry. So the definition of trivial. Okay, trivial means something a little bit technical here as well. What I mean is that the field content on the wire that's interacting with the photons, they're basically free fields or some generalized version of them. So that if I want to calculate any correlation function of these free fields, I can use Wick's theorem. I can just contract them pairwise. There's no very interesting dynamics of these fields on the wire. That's the technical meaning of this trivial statement. Okay, so why might you care about any of this? And that's what the first half of my talk will be about, to try and get you interested in this topic and show you some of the connections to ADS-CFT and so forth. So there's a basic theory question, I think, that it's interesting to know if you have a coupling of this form, you couple the gauge potential to a charge current. It's interesting to know whether or not that will produce anything interesting in your theory, whether it will just gap out at the end of the day and you have just two separate universes, the universe on the wire, the universe in the bulk, no communication at the end of the day. That's possible. Now, I think there are also some applications, and I'm a little bit embarrassed to say I still haven't really done my homework here and read deeply into this literature, but I think it's pretty clear that for people in the condensed matter community who are interested in quantum wires, so those are reduced dimensional systems where the degrees of freedom on this wire really feel that it's a one-dimensional system, that the result here should have some implications for those kinds of systems, especially when you have, I don't know, nodal metals where the electrons cross the Fermi surface. There's some basically massless states on this wire. And I think there's also probably room for applications to cosmic strings in cosmology. Universe is cooling in the distant past, some defects form because the whole system can't relax effectively uniformly throughout space. You get these defects, and you may have some massless degrees of freedom, some massless fermion zero modes that are trapped on the string. And it's, again, interesting to know how those may or may not communicate with the stuff in the bulk, the free degrees of freedom that make up the universe. But there's a larger story here. Those are kind of the two obvious things, but there's also a larger story here that I'd like to tell you before getting to the kind of technical details of this proof, which I hope will motivate you to listen to the whole talk. Okay, so let's get started. First half motivation, second half technical details. So I come at this from this idea that, or I've been very interested in this notion of defects and boundaries in theoretical physics for 4 or 5 years now. And it sort of occurred to me thinking about it that they're really very important in seemingly rather disparate areas of physics. And I've drawn a couple of pictures here to just point that out. I mean, they're D-branes in string theory, which are boundary conditions for open strings. D-branes are clearly a very important topic for string theorists, and maybe more broadly, giving us insight in non-perturbative dynamics of these string theories, dualities, and so forth. Probably don't need to tell this audience that boundaries are very important in the ADS-CFT correspondence. So here's my cartoon picture of a black hole sitting in, I don't know, global ADS. So what is ADS-CFT? It's a map between a theory of gravity with some kind of boundary and a field theory in one dimension less. And the boundary on the gravity side is in some sense where the field theory lives. So again, in ADS-CFT correspondence, boundary is really playing a very central role. And I'll try to make this a little bit more precise as we go forward in the talk. Here's a picture of the spectrum for the electrons in a topological insulator. These are materials that are gapped out in the bulk, but they're surface states that cross the Fermi level, and those massless states here are protected by discrete symmetries. And again, the boundary in this notion of topological insulators is playing, I think, a really central role in this field that's been very inspirational for many people in the condensed matter community. So there's all that. And then finally, if that wasn't enough, there's also people interested in quantum information. In particular, they want to think about entanglement in many body physics. I know we already had a couple of talks about twist operators. So twist operators are a really good thing to learn about if you want to compute entanglement in field theory. And the idea is you put some twist operator down on the boundary of a region, and by analyzing the partition function in the presence of that twist operator, you can calculate the entanglement between two regions. And so again, I guess that's maybe how I came to the subject most directly, I started thinking about entanglement and quantum information aspects of ADS-CFT, and then I realized most of the really important results I cared about in this field were all tied up in the physics of boundaries, the boundary between two regions I was supposed to be, I had introduced to calculate the entanglement entropy. So these four things, I think, are they're sort of huge developments in theoretical physics, and in all four of them, boundaries and defects are playing this really central, huge role. And that's all sort of general nonsense. Let's try and make it a little bit more specific. Let's focus on ADS-CFT, especially since this is a conference in ADS-CFT and holography. More generally, what are the lessons? What are sort of some of the deeper lessons from ADS-CFT? I think one of them is that extra dimensions give you insight into strong coupling physics. Just from the statement of the original correspondence, we have the statement that strongly interacting n equals 4 super Yang-Mills in 4 dimensions. We can learn about that by studying a string theory in 10-dimensional space. And maybe one way of motivating what I'm doing here is the question, can you get rid of gravity on the right-hand side and just replace it with a defect or boundary quantum field theory? And I know for some people in the audience, this is anathema. They love their black holes. Black holes, I admit, they're really cool. And when I do this, I'm kind of giving up the black holes, and I'm kind of just focusing on zero temperature physics, sort of the probe limit of ADS-CFT, if you will. But still, I think there's a lot that we can learn about just by thinking about ADS-CFT without gravity. And I'll just make a remark here. You think about this theory, this type 2b supergravity or type 2b string theory on ADS5 cross S5. The way it's often motivated, right, is you take some stack of D3 branes and you say they're really heavy and they warp the space-time, and then the space-time becomes ADS5 cross S5 when you get close to the D branes. But there's another thing you can say, which is that by Weil rescaling the metric of ADS5 cross S5, you get precisely a 10-dimensional system with these 4-dimensional defects, which are D3 branes. And whenever you have a conformal field theory, these Weil transformations are under very good control because the parent curved space theory from which this conformal field theory comes has Weil symmetry. And so at some level, when you give up gravity on this side of the correspondence, you are really studying defect conformal field theory in flat space. Okay. Let me give you a specific example, sort of maybe the flagship example. This is a purely quantum field theory analog, I feel, of the ADS-CFT correspondence. And it's very simple. It's very simple. I learned about this reading sort of orthogonal papers. I think I came across this by reading papers by Tabor and Kodakov, who I'm not sure they're the first to point it out, but they used it extensively in their work. They were thinking a lot about graphene at the time. So what is it? So on one side, we're just going to have a very familiar character, 3-dimensional quantum electrodynamics. Okay, so it's got a 3-dimensional photon. It's got a 3-dimensional fermion. In fact, it's got NF of them, so there's a lot of them. And on the other side, what I want to take is a mixed dimensional system, so a system with a boundary. So there's going to be a bulk 4-dimensional photon, but there's going to be a boundary 3-dimensional electron. So this is very much like graphene, right, where you have a sheet of carbon atoms on which the electrons are constrained to move, and then they interact via photons that are ambient in the 4-dimensional space. Okay, so there's going to be a boundary condition that sort of encapsulates this interaction where the normal tangential component of the field strength interacts with the charge current of the electrons. And the claim is that there's a duality between these two systems that's very much like the ADS-CFT duality. Okay, oh, right, then I have the covariant derivative, right, which is the ordinary derivative, and a piece that comes from the gauge field. So how does that work? How do you see that? So let's do a kind of Feynman diagram type argument. We're just going to map the Feynman diagrams of one system to the Feynman diagrams of the others. This is like a perturbative type equality. So the photon propagator for mixed dimensional QED. What I want to do is I want to try and understand how the electrons will scatter off each other by kind of integrating out the bulk physics for the photon. So one way to do that is to think about a Fourier transform. So typically, right, the photon propagator in 4 dimensions, or actually in any dimension, it's going to go as 1 over p squared. But now, because I've lost translation invariance normal to the boundary, so I just have my boundary, and then there's a normal direction here. I don't want to do the Fourier transform over that normal direction, and so because I've done one fewer Fourier transform, I wind up with one fewer power of the momentum downstairs in the denominator. And then I still have this distance. It's encapsulated there in some exponential fall off as I go away from the boundary. But if I'm thinking about scattering processes on the boundary, I don't really need to worry about this at all. I can just replace it by its value on the boundary, which is 1. And so the propagator for the photon, this is a long way of just saying the propagator for the photon is just 1 over the momentum. Now let's compare that with what happens in 3-dimensional QED in the large flavor limit. So what you can do is you have that p squared I was just talking about, and then you want to resum sort of the leading large N effect, which comes from this self-energy term, pi of p, which looks like this. So it has a factor of NF, a factor of E squared, and a factor of 1 over p in the denominator. And now clearly if I put this in here and I look at low energy processes, so the low energy limit fixed point type theory for this 3D QED, I'll cancel out one of the p's with the thing in the propagator. The NF term here will make it dominate since NF is so large, and this propagator in the large NF theory will go over to 1 over p in the large NF and low energy limit. So it's the same propagator. And then we can pay attention a little bit to the factors of NF and E and so forth. And we see, what do we see? We're going to get something like 1 over NF E squared as well from that propagator. But then when we build our diagrams, so we're going to what? We're going to scatter an electron off a photon. And so we're going to have some factors of E at the vertices. And so when we package that all together, the factors of E will cancel in the vertices with the factor of E squared downstairs in the propagator. And we get to see here from this kind of scattering process, we want to compare that to what happens upstairs in the mixed dimensional theory, where again, you have this kind of thing. But now I have 1 over P and G at the vertices. So I want to compare G squared over P with 1 over P, 1 over NF. Okay, and so do this a little bit more carefully, and you can see there's kind of a perturbative equivalence, well, resummed on the large NF 3D side, that maps all the Feynman diagrams in this mixed dimensional case to the Feynman diagrams in the 3D case, with this particular identification that 1 over NF is G squared, which is very familiar to people who love ADS-CFT, who know that like 1 over the number of colors squared is G string. It's a very similar kind of relation. Okay, so I thought that was very neat when I saw that for the first time. And in fact, this theory has a number of other really special properties that gotten me kind of excited over the years. So here it is again in all its glory. It's got my 4-dimensional photon, my 3-dimensional electron. There's a relation to graphene that I was mentioning before. That's the statement that Well, graphene isn't conformal. Graphene has beta functions, and it's also not relativistic. But there's a claim that if you follow graphene to its RG fixed point, there's a sense in which it will land precisely on this mixed dimensional QED, that the speed of the electron will gradually increase. There's a beta function for it until it matches the speed of the photon. The magnetic interactions will be restored, and this guy is the ultimate IR fixed point for graphene. So that's one really kind of neat thing about this theory. There's the relation to large NF QED3 that I just pointed out. It has, maybe not surprising, some nice behavior under electric magnetic duality. You can relate the strong coupling version of this to a weak coupling version of it and use that to further constrain scattering processes. That's something that Sun and Shao did a few years back. And then there's stuff that we've been working on, one of which I'll show you in the next few slides because I can't help it, even though it's kind of a distraction from the main thrust of the talk. It is indeed a conformal field theory. And in fact, it has an exactly flat direction. This coupling G, there's no beta function for it. That's a consequence of gauge invariance. It really does have conformal invariance. There's a very interesting story with conformal anomalies that we've been working out. There are supersymmetric versions, which means that you can then use this notion of supersymmetric localization and get exact results for transport, which is something I used to get very excited about when I used ADS-CFT correspondence to study strongly interacting systems. And so that's what I can't help showing you before we get to the technical details of the talk. I can't help showing you. So this is this mixed dimensional QED, so 3-dimensional electron, 4-dimensional photon, and now we make it supersymmetric, so we add some super partners, and we use some localization. It's a long, another technical argument that I can't get into today, but you can read all about it in this paper we wrote a couple of years ago before the pandemic. And here it is. Here's the y-axis here is the conductivity. For different kinds of U1 symmetries in this theory. This theory actually has more than just one U1 symmetry. And the x-axis here is the coupling, right? If I take the log of the imaginary part of tau, that's going to depend on this coupling strength G, this marginal direction in this theory. And using localization, I can compute the conductivity for any value of the coupling. In particular, I can compute it for 1 values, which I think is really kind of a remarkable thing about this particular theory. I don't think I know too many other examples where this is possible. So this is just one particular example, which has some number of different kinds of chiral multiplets on the boundary. These ends refer to how the chiral multiplets, the matter on the boundary is charged. And here's just another example where we change the matter a little bit. And again, you can get these exact conductivities. And here I've introduced the small theta angle and looked at the conductivity in that case as well. So you can break CP. Is there any bound on the conductivity in this model? Not that we saw. I'd like to get back to it and look at it more carefully. I think there's more to do here, but I've been distracted by other things. What is very nice about it is that there's a nice story about S-duality. And so these theories transform under S-duality. This particular one is self-dual, and that starred point is the self-dual point, which in this plot just looks like any other point on it, just somewhere in the middle. But no, it's an interesting question. Yeah, I should probably stop here and ask if there are other questions too, because I think at this point, the talk is going to start to get a little bit more technical. And I think I'm also running ahead. I usually anticipate more questions. No? Okay. Again, just write something and I'll try to answer it as we go on.
Yeah,
oh, right. There was
you want
go ahead. Yeah.
Question? You want to answer the question? Please. If you want, yes. There is a question from Prof. Kazem Fadafan. Is there any bound
about
conductivity?
About the bound on the conductivity. Yeah, I saw that question, and I don't know. I can try to say what I was just saying again, is that I think there's more to do with this theory. There may be some interesting bounds one can prove. I don't know them. I think one of the most interesting things about this theory is the imprint of S duality, which exchanges this strong coupling version with a weak coupling. And you can even investigate the self-dual point here for this particular guy, which you might, want as a point of minimum or maximum conductivity in some appropriate sense. But I don't know. I don't know. I don't know the answer to it. Maybe there's another way of plotting this data where this looks like a local extremum. It's a great question. I don't know. Okay. Great. So there's another example I want to talk to you about, which I forgot that I had in this talk. So this is a more recent example, and this is not something this is actually other people's work. I mean, we were very interested in this kind of class of models, my old student Kuo-Wei Huang and me back in 2017. And then there's been a lot of work on this kind of stuff since then. But I thought there was this very interesting recent paper by Connor Behan, Lorenzo Di Pietro, Eduardo Loria, and Bolt van Ries. This guy's great, by the way, and he's looking for a postdoc. So if someone has some money, they should hire him. So I want to talk about this work here, highlight this work, because I thought it's really kind of another really nice example of a boundary conformal field theory where maybe you have some control and can do stuff and maybe even learn about strongly coupled physics. So let me show you how that works. So the example before had a free photon in the bulk and charged matter on the boundary, which could even become strongly coupled, and we could still learn stuff about it. The model now is going to have a free scalar in the bulk, free scalar field. That's this guy phi. And it will have something on the boundary, which we'll try to make more specific as we go forward. So the trick, or the idea here, is to take the boundary value of that scalar field and couple it to something on the boundary, this operator O. And you could imagine maybe having Dirichlet boundary conditions, in which case phi will vanish on the boundary, but you can still couple stuff to the normal derivative of phi. Or you could imagine having Neumann boundary conditions, in which case dn of phi would vanish, but you could couple things to the boundary value of phi. And what I want to do here is I want to couple it in some way that I'm going to have control. Now this is the part where you have to have a little bit of inspiration. Maybe you can make these very slightly relevant so that these are weakly coupled. These couplings are small. Maybe it won't flow too far, and it will quickly get to some kind of renormalization group fixed point where you have control, perturbative control of what's going on. So that was the idea. And then maybe once you have a model like that, you can push on it a little bit and learn about what happens at strong coupling. So their inspiration was, well, since if we have, for example, a 3D scalar field in 3 dimensions, then the boundary would be 2 dimensions. And maybe a good place to start would be this whole literature on 2-dimensional conformal field theory. And a very nice class of models there, the so-called minimal models, which have central charge less than 1. And they're very well known, very well characterized. Their spectrum of operators can be summarized in this rather simple looking equation. So you introduce the MPQ, so-called diagonal minimal model, and it will have operators phi rs with these scaling dimensions, and r is some integer that goes from 1 to q minus 1, and similarly for s. So probably a lot of you know this well. This tends to get taught in conformal field theory classes, so it's well-known stuff. And then what they did was they said, let's look at the case m plus 1, when m is huge, and expand the dimension in a power series in m. And there's a leading term and a subleading term, and hopefully we won't have to worry about anything more, at least in this initial analysis. And we can identify a couple of interesting operators. We can look at, say, phi 1,3, for which the leading term here is 2, so marginal. Remember, we have d2x integral phi 1, 3. So that would be a marginal operator from the 2D boundary point of view. Or you could look at phi 1, 2, for which this would be 1/2, but I can couple that to this operator, right? So the partial n derivative, that's a 1, and the phi, that's a 1/2, weight 1/2. So this thing has weight 3/2, and this thing altogether would be just about marginal. Now I wanted it to be marginally relevant, not irrelevant. So probably I should switch the order of the RS's, and then I can change the sign of the second term. And let's, as a first pass, let's take a look at these two operators and see what happens. And that's what these fellows did. And it was a good idea. So it turns out when you add these two operators to your free scalar field, phi 3, 1, phi 2, 1 coupled to dn phi, you can quickly establish that there's a fixed point in conformal perturbation theory where you have control over the endpoint, where the coupling H star has this expansion in 1 over m. It remains quite small in the large M limit, and similarly for G star, and you can go further and you can compute anomalous dimensions. And then what made this work really special is that they were able to really push this into the non-perturbative regime by doing the conformal bootstrap, by bootstrapping the boundary correlation functions. And they were able to see precisely these theories in their numerics, and then they were even able to go to general M and see what happens as M gets smaller and smaller and smaller. So I thought that was really kind of a neat project. I wanted to advertise their work a little bit. Okay, so now we're getting to the end of the motivation. So unlike ADS-CFT, we're moving away from classical gravity. Well, this is a little bit of hyperbole, can entail much pain and suffering. I think there's a clearer path here. I mean, on the ADS-CFT side, you really have to worry about, you start with, I don't know, classical supergravity, and then do you really want to, push that into some stringy limit or some quantum gravity limit? Because that's what you really need to do to walk away from the infinite strong coupling region on the field theory side. And we know that in certain cases we can do this, and there's been a lot of progress with the quantum spectral curve for n equals 4 super Yang mills and so forth. But I think this sort of pure QFT point of view may be a little bit simpler. I don't know. Simpler with a question mark. Because if you set things up this way, you have sort of two clear paths that you can use. You can use localization, as I showed you these two plots a few minutes ago for the mixed QED theory. We made it supersymmetric, and then we were able to compute certain observables like the charge conductivities exactly at any order of the coupling. So I thought that was really kind of remarkable. And then you can also use the conformal bootstrap, which these fellows did for this free scalar field coupled to a minimal model. And again, walk away from strong coupling physics, from the weak coupling limit, and learn a little bit about strong coupling physics on the boundary. So this is all boundary physics, and there seems to be a reason for that. It turns out if you want to start with some free degree of freedom in the bulk and couple it to a defect in higher codimension, so not just a boundary, but like a line or a point or something, it seems to be much more constrained. So we have a result from a couple of years ago, or I guess just 1 year ago, from the same group who did the minimal model example I talked about a few minutes ago, where they proved that if you have a free scalar in the bulk and a defect with codimension greater than or equal to 2, so precisely not the boundary case, that it has to be trivial in exactly the same sense that I'm going to argue this conformal surface defect is trivial for Maxwell theory. That this work is an analogous claim, and in a sense it's just a follow-up of this paper, which I admire, for the surface defects in 4D Maxwell theory. And then I think it's quite likely that you can make similar claims for other free systems, that you could make a similar claim, for example, for a line defect in Maxwell. Like if you had a Wilson line or Twift line or something, it would have to be similarly trivial. I believe it's also true for free fermions in codimension greater than or equal to 2. And if you want to push on this Maxwell theory a bit, I guess you have to replace it with a p form and 2p plus 2 dimensions. And you could prove that that's invariant also. Oh, there's another question. Is chirality of the fermions important? I'm not sure. What's the context in improving the freeness? Or, sorry, improving the triviality of the theory, or? Is the chirality of the fermions important for the model? So which model, though? That's what I guess I'm not understanding. In this case, I have no idea. That would be really fascinating if there was some further constraint based on, I don't know, chirality or reality properties of the fermion. For the supersymmetric case, the localization model I was talking about, this mixed dimensional QED, there it's all very constrained by n equals 2 supersymmetry. So the chirality is sort of what comes out of insisting on n equals 2 supersymmetry. So it's curious that the boundary case is special. It is curious, and I'm not sure I have a simple explanation for what makes the boundary so special in this kind of framework. All right, so that is the end of the first part of my talk. And the second half, I'd like to show you the proof. So it's about to get a bit more technical, but I hope now you're kind of motivated to see what goes into the proof and to see why it might be true. Oh, I forgot. I have a really simple back of the envelope argument for why it's trivial. So let me give you that first, and then we'll get to the technical details. So this is a kind of perturbative argument for why a surface defect in Maxwell theory is trivial. So we want to think about, scattering of electrons via photon, and what is the effective photon propagator that's experienced by this charged matter? So now we're not on a boundary anymore, we're on a line. For the boundary case, we saw that the propagator was 1 over the momentum, that we Fourier transform 1 dimension less. So instead of 1 over p squared, we get 1 over p. Now, if you have a surface, or 1 plus 1 dimensional defect, a wire, you're Fourier transforming 2 fewer space-time coordinates. And so that means instead of getting 1 over p squared, you get log p. And so already at tree level, when you're computing these scattering processes, you have to introduce a scale, an effective scale. There's sort of a dynamically generated scale to regularize this log. And I think that's a really cheap and easy way of seeing what the problem is with these theories. Of course, it's a perturbative argument. It's not, I'm really relying on my perturbative intuition and scattering processes and so forth. But this is something that immediately goes wrong when you try to think about a weakly coupled version of a charged matter on a wire interacting with a photon in some conformally invariant way. You have this log that it makes you introduce a scale. But we'd like to be a little bit more rigorous and non-perturbative, and so let me give you an argument that's just based purely on symmetry. So I'll pause again and ask if there are any questions before we dive into this. All right, here we go. So there are 3 steps in the proof, and it goes like this. So I have a Maxwell field in the bulk, and what I want to do is I want to kind of expand it out in a Taylor series in terms of modes on the boundary. This is called the defect operator product expansion, or defect OPE. And when we do this, because the field is free in the bulk, because it satisfies Maxwell's equations in the bulk with no interactions, it's very constrained what can show up on the boundary in this decomposition. One finds two scalars, so L equals 0, no angular momentum, and a tower of vectors with L equals plus or minus 1. So that's the first step, to show that. Now, once you've showed that, we're going to compute a 3-point function of the Maxwell field in the bulk and two boundary operators, W2 hat, W3 hat. And we're going to find that this object, because F is free, is almost always sick. It will blow up in a way that's not physical, somewhere in the bulk where it has no business blowing up. And because of that, there's very severe restrictions on what you can put in here and expect to get something sensible from. So it's very severe. Said in another way, there are very severe restrictions on what kinds of fields in the defect can interact with the field in the bulk. So what one finds is that, let's just assume that the scaling dimensions of W3 are larger, and W3 has to satisfy a double twist condition. So it has to, you have to be able to write it in the following very restricted way in terms of the operator dimensions of the other two guys. So H2 gives you the scaling dimensions of W2 and H1 of the operator O hat in the defect OPE decomposition of F mu nu. So in other words, you're restricted to looking at 3-point functions where W3 hat looks something like operator in the defect OPE of F, some number of derivatives acting on W2 hat. That's the only thing that can show up. This is what I call a double twist condition. And then given that, in the third step, we use that to show that if you want to calculate a correlation function of these O's, you can do it very simply just using Wick's theorem. And so there's really no dynamics in the theory. The stuff on the boundary is basically free. So those are the 3 steps of the proof, and now we'll go through them one by one. So step 1. So we use conformal invariance. We're using symmetry all over the place here. The conformal invariance of this model is going to fix these 2-point functions, the 2-point function of the field strength with a boundary operator and the 2-point function of two boundary operators up to numbers, up to constants. There's also going to be a constraint on the perpendicular spin. So there's also, we have this SO2 rotation around the wire, which is characterized by some spin quantum number I'll call S. And so that always has to vanish when you sum up the S's in the correlation function. Okay, so we have free field constraints. D mu F mu is 0. D mu F dual is also 0. And that gives you a bunch of differential equations that this 2-point function has to solve. And when the dust settles, you basically find that you can decompose F into a sum of operators, O hat, where O hat is either these two scalars or this tower of vectors. And again, the way to kind of show this, right, if you have very strong constraints on this, you can always just take the 2-point function on both sides. You put a W hat in here and a W hat in here, and then orthogonality of the 2-point functions on the boundary in the bulk restrict what has to show up here. So in a little bit more detail, this is the full form of the defect OPE for F mu nu. So I lied a little bit here. You don't just get the two scalars, pi and tau, and the tower of vectors, psi and phi. You also get their descendants. So in conformal symmetry, you have the primary operator and all its descendants in the multiplet, and the defect OPE has to include those descendant operators as well. But we can get those, at least formally, through these differential operators, D, A, B, and C, D, acting on the primaries. Okay, so this is the full defect OPE for F that we worked out for this model. Now, a few more remarks about the defect operator product expansion. You might be interested in what these differential operators actually look like. They're not actually that bad. They depend on some sum over derivatives. These W derivatives, W is along the defect, and then Z is transverse. That's why the Z to the S is there. That S is the transverse spin. And the other operators B, C, and D are similar. And also, I'm only giving you one of the 6 components, right? This has indices, so there's 6 different choices of indices there for A and for all the others as well. At any rate, to recap, this form is fixed by consistency between the bulk defect and the defect 2-point functions, conformal invariance, and the free field equations for F. So that's the first step of the proof, to establish this defect OPE and what kinds of operators are in the defect OPE of the Maxwell field. And there's some differences already from the boundary case, which maybe explain a little bit why the boundary is so special. So I omitted something in the discussion so far. I've been using an additional condition here that I haven't said anything about. I'm using reflection positivity, or unitarity in the Lorentzian case, to constrain the form of the defect OPE. So without the reflection positivity, I actually would have found a couple of different options for the dimension of these vector operators, psi and phi. So I found that they were 1 plus S. But in fact, 1 minus S is also allowed if S is positive. But there's this unitarity bound or reflection positivity bound. So if you remember right, the engineering dimension of a conserved current should be what? D minus 1, right? Where D is the number of dimensions. And here I have a 2-dimensional defect. And so the conserved currents should have dimension 1. And that should saturate the reflection positivity bound, those things which have these shortening conditions. And so the reflection positivity bound allowed me to restrict delta to be greater than or equal to 1. And I used that in this decomposition. And at a similar stage in the scalar case, it's a bit different. One finds an analog of the minus choice here, delta 1 minus S, is not below the unitarity bound. So you get some extra scalars in the defect OPE of the bulk field, which allow for some extra flexibility at the second step. And similarly for mixed QED, there's a pair of boundary conserved currents, whereas here we basically just have one choice. This is very closely related to the phenomenon of alternate quantization in ADS. I mean, you guys, ADS CFT folks know this well, right? You have this result for the mass squared times the ADS radius squared is what? It's delta times delta minus D. And so for any given mass in ADS, you have 2 choices of dimension. This is the Weil rescaled analog of that. It's precisely the same kind of condition. In this particular case, we only have the one quantization. Everything else is below the Brighton line, or is below the unitarity bound. Whereas for the scalar, there's an additional choice of scaling dimension in the boundary case. All right, onwards and upwards. Step 2, I wanted to analyze this bulk defect 3-point function. So this was a real mess, and this is what really held up the paper for months and months and months. I think we thought we could get away with just some back of the envelope arguments at the beginning about how this was supposed to behave. And indeed, the conclusions we wanted to draw from this never really changed, but we realized that the arguments that we were using to get there were very weak, and we really had to just go back and compute this thing from scratch, and it took forever. It's a rather complicated looking object. So it depends, so you're using conformal symmetry to constrain this object. It depends on 6 weight 0 tensor structures and 6 functions of an invariant cross ratio. So already with 1 bulk and 2 boundary points, you can construct an invariant cross ratio from the locations of those operators. This is a little bit different from regular conformal field theory, where you need at least 4 points to get a cross ratio. Here with a boundary, 3 is enough if 2 of them are on the boundary. And then there's this prefactor, which we will encode the S, L2, and L3 dependence, the rotational angular momentum type dependence of the correlation function. So it's a real mess, but the procedure is kind of straightforward. There's 2 obvious things we could do. Well, I gave you a way of decomposing F into boundary operators. So you could just substitute that defect OPE into this guy. And now I have 3 defect operators, 3-point functions that involve 3 defect operators. Those are fixed up to numbers in the usual way they are in conformal field theory. And so in principle, you could do this sum and get this object. Or another thing you could try is you could apply, the free field equations to this bulk defect guy and see what the constraints are from that are. And in principle, that should also give you the same answer. But in both cases, there's some issues. In the first, it actually turns out to be rather difficult to compute those sums in closed form. And in the second case, you have a bunch of differential equations, and it's hard to understand the boundary conditions. But we found that by putting these things together, there was enough information to sort everything out. And we could completely specify the form, or at least specify it enough that we could make some rigorous arguments based on its form. So remember, I had these 6 functions of a cross ratio, F1, 2, 3, 4, 5, and 6. Here's just one of them. I think it's one of the simpler ones. It depends on the following hypergeometric function. That's what this 2F1 is there. Really quite a mess. And it's also a function of this, it depends on this cross ratio. And there's an overall constant out here, which is fixed by 3-point functions of the boundary fields or defect fields. And now the issue with this guy is that you may recall that hypergeometric functions have 3 singular points, basically at 0, 1, at infinity. And one of these singular points is going to lead to rather non-physical behavior in this case. So what I want to look at is I want to look at the point u equals 1. So when u equals 1, that turns out to be the following configuration. I take 2 of the insertions on the boundary, I draw a semicircle that connects them that goes into the bulk, and I put the 3rd operator somewhere on that semicircle. And so whenever I do that, u will be equal to 1. But from our defect conformal field theory point of view, there's absolutely no reason for anything bad to happen there. And this isn't really an issue about like radius of expansion or radius of convergence in a sum or something. I mean, this is just one term. It's not like we're summing anything. This is just, one operator on the boundary that's basically in the defect OPE of F mu nu that's contributing to this 3-point function. It's not like we have to sum over anything to get at this. So I think the only obvious way to get rid of this non-physical singularity is to restrict the spectrum. Now, so we have this hypergeometric, and again, another fact you may recall about hypergeometric functions is that whenever one of these first 2 indices is a negative integer, they have a polynomial form. So we'll take advantage of that. We'll set those scaling weights to negative integers, one or the other. And then it turns out since the angular momentum L2 and L3 are also integer, that will imply a condition on the other guy. So if I put a condition on H3, this guy will put a condition on H3 prime, or vice versa. And then finally, you can recognize the 1 and the n in here as being related to the scaling dimensions of the operators in the defect OPE of the field strength. So when the dust all settles, this is precisely the double twist condition that I had in the summary of the proof a few slides ago. Okay, so that I think is second step, and now I'll just point out a few differences from what happens in the boundary case. So in the boundary case, I remember we have this alternate quantization that we can take care of, this other mode with dimension 1 minus s. And it turns out that by tuning the appropriate 3-point function coefficients, you can kill this singularity at u equals 1. So this extra mode or extra field, extra possibility of having a field obeying the unitarity conditions allows you to get rid of the singularity without restricting the operator spectrum in this very severe way that I did on the previous slide. Okay, so you had that, and then you wouldn't necessarily have to have these double twist operators. All right. Okay, final step, the contour integral argument. This is the picture on my title slide. We're going to use induction here. Well, we know 1-point functions on the defect vanish, and we know 2-point functions are fixed by conformal invariance up to some number, which we can normalize to 1. And let's assume we can compute an n minus 2-point function. And let's show that we can compute an n-point function. That's the strategy of the proof at this point. So what's the relevance of this double twist condition? If I look at the operator product expansion of two boundary fields, so I'll bring W1 hat and W2 hat close together, then I'll get a contribution from the identity. That's the fact that they could have a 2-point function. And then there'll be a whole bunch of other possible primaries and descendants that show up in that OPE as well. But because of the double twist condition, the exponents here are very highly constrained, right? I have to have that h1 plus h2 minus hk is minus an integer, and similarly for the primed h's. And so when I plug that in here, right, the w comes upstairs, becomes a positive integer power of w, and there'll be no branch cuts in this sum. And so if I want to think about the discontinuity in the commutator of these two boundary fields, it's completely determined by this first term, by the identity operator contribution. Okay, and that will be the key observation in this contour integral argument. So here it goes. We'll introduce our n-point function with n boundary fields. We'll put n minus 1 of them on the real axis in the w plane. And we'll take the first one and we'll put it out here somewhere. And we'll actually take W1 bar. We're going to break the rules of complex conjugation a little bit. We'll keep the complexified tau component not complex conjugated and just complexify or take the conjugate of the y coordinate. At any rate, we go through this argument and we're going to find branch cuts whenever these insertions get close to each other. So in particular, when W1 minus WK is 0, which is equivalent to tau plus IY minus tau K equals 0, which means I'm going to have branch cuts whenever tau is tau K plus or minus IY. Okay? So basically, I'll have branch cuts that come up and down from these points on the x-axis where I've located all these other insertions. So here's the picture. Here's the caterpillar, the hungry caterpillar contour with the branch cuts here going up and down the y-axis or parallel to the y-axis that I'm going to have to avoid. That's when these two operator insertions get close together. So I'll take a little integral around tau, and then I'll puff it up into the red integral, the caterpillar integral that goes around the contours, and then I'll puff it up even more into these blue lines that go up and down on either side, avoiding the cuts. And when I write it in that way, as these blue lines, I can replace those blue lines basically with commutators of the different pairs of operators of W1 with W2, W1 with W3, and so forth. And then finally, I'll plug in what this commutator is, the fact that it doesn't have these complicated structure. It just depends on this identity operator term. So I'm able to do this contour integral very simply. It reduces to this guy, which is a restatement of Wick's theorem that the endpoint function depends on a sum of n minus 2-point functions, or I pairwise contract W1 with each of the other possible operators. And we've done this for specific locations, but we can extend it to arbitrary positions by considering descendants. And basically descendants is some Taylor series expansion around the positions we selected in the proof. Anyway, it goes through, and this is not really an original argument. I'm copying this more or less word for word from the Loria et al. Paper that I cited a few pages back. So some concluding remarks. I know I'm kind of out of time. The theories that are free in the bulk and interacting on the boundary, or defect, I think they can be nice, interesting, tractable examples of strongly interacting quantum field theory, where the strong interactions are on the defect. There seems to be a conjecture that free in the bulk theories in codimension greater than or equal to 2 are always trivial, or we've seen a proof for the Maxwell case. I've cited a proof for the scalars, but it looks like it may go through more generally. And there's some clear future projects which involve, for example, proving the line defect in Maxwell is trivial, or free in the bulk fermions with codimension greater than 2 are trivial, or also possibly bootstrapping this mixed dimensional QED theory, which hasn't been done yet. It's another project I'd like to get started on at some point if I can find enough manpower. Right. Very good. Thanks.
Thank you so much for Christopher for your nice talk. And we have time for 2 short questions or one long question. If there is any question, please raise your hand and I will let you know to ask your question.
Or I guess they can just type it in the chat too.
Yeah, yes. And
yes.
Thanks
for your interesting talk. I asked my question in the chat actually, but at the end I was going to know more about the transport properties of this strongly coupled fermions that are living on this defect actually. You showed some plots about the conductivity, but I'm curious to know, is there any special effect that is weird here, is strange here?
Any special effect? This was the mixed QEDs. This was the boundary, 2 plus 1 dimensional boundary and 3 plus 1 dimensional photons. Is there any? I think there's more to do. I don't know. I mean, we looked at a couple of models using this localization, and then I kind of put it aside. And one of my collaborators went on and he computed some 2-point functions involving the stress tensor as well. So stress tensor current, I guess that can give you a thermoelectric effect, or stress tensor, which could give you some heat conductivity. You can also get at these apparently through localization, which I think is pretty neat. And then the other thing I mentioned during the talk was I think there's a nice story about self-duality, which probably can be elucidated further.
I asked this question because of the wild semi-metal that you put in one of your slides. Actually, if we consider anomaly, then it would be possible to see some strange behavior for fermions. I was wondering if such phenomena exist in this theory. In that case, we should add some time reversal terms to break actually time reversality. I was thinking that if adding such terms would affect the results or no, that's trivial.
So we can add a theta term. Maybe that's not, I guess that's CP, right? Maybe that's not quite what you want to do. I don't know. Is that good enough, the theta term, or? Because that's part of what was done here with, like, the real part of tau is 1/2. That's where you add the theta term. That will break some of these discrete symmetries. But yeah, I guess it's actually on my to-do list. My colleague here, Andy Sturgio, was actually asking me a similar question yesterday, whether I wanted to do something with Weyl fermions on line defects, and how they might lead to current non-conservation in the bulk. But that's that's a project at the very, very early stages where I still need to do some reading in the literature.
Okay, thank you. And I have one very, very quick question. My question is, if one consider instead of if mu nu as abelian terms, instead of them, if one consider Yang-Mills theory, what happens to this theory?
If I consider Yang-Mills theory?
Yeah, instead of F mu nu, which they are abelian, and so they can commute, but we consider some non-abelian theories. What happens to this?
Yeah, excellent question. So it gets much harder because, of course, non-abelian theories are not free in the bulk, and I can't apply just the equations of motion and get as simple a story. But they are, I mean, there has been some work, for example, looking at n equals 4 Yang-Mills with a boundary using localization. There's a nice paper by a fellow named Chris Waddell a few years back, and other work too that I'm not remembering to cite at the moment.
Yeah, and thank you. And maybe time is over, and so let me applaud you again, and thank you so much for your nice talk. And maybe we can keep touch then